Okay, chemistry, we're on to our third lesson in the acids and bases unit. This is going to be one of our longer units, and this is the lesson on weak acids. So let's review generic acid notation. We've seen this earlier. So write the reaction of the dissociation of benzoic acid. And if you don't know the formula for benzoic acid, you can write the reaction in generic form. So that's why we use the generic form, because there are tens and thousands of weak acids. You can't possibly know them all. But if you know the 7 strong acids, and you see an acid that is not one of those 7, then you know it's a weak acid. And all the reactions behave the same. So it would be HA equals H+, that's the proton, that's the hydronium ion, plus the rest of that HA molecule, which is the rest of it plus the electron that the H left behind. Remember, the H is just a proton. It was a hydrogen atom that covalently bonded to another atom or molecule. And when the proton and electron, and when the proton was pulled away, the electron was left behind. So that leaves a negative charge on that A part of it. The H+ is simply the proton. Or you can write it in the expanded form, which is HA plus H2O produces H3O+, so that H jumps over onto the H2O, the water molecule, to make it a hydronium, H3O+. Remember that H+ and H3O+ are exactly the same thing. And then at the end you also have the A-. As long as you have the necessary values for the concentration of Ka, you can analyze the reaction for benzoic acid without even knowing its formula. So let's look at a few more examples. So here are a few more examples of Arrhenius and Bronsted-Lowry acids. The definition for acids for those two types of acids are the same. Okay, so here's HClO4, and that's going to break off. The proton's going to come off. That's the H+. And what you're going to have left is the rest of that molecule, which is the ClO4 with the electron that was left behind. So that's the A-. So you can see how that would be written in generic form. Or here it is the same reaction in expanded form, so it's HClO4. That is going to donate the proton to the water molecule, H2O. That's going to produce H3O+, and then again the ClO4-, and there you see the generic in the expanded form. HA plus H2O produces H3O+, and the A-. Here's nitric acid, HNO3 is H+ and NO3-. So that's going to give you an HA over on the left, and the H+, and the A- is the rest of that molecule after the proton has left. So how do Ka and pH values compare? So we're going to review this because we're going to deal with both of these concepts quite a bit. So a 6th grader can lift 5 skateboards up onto a shelf. A 12th grader can lift 10 skateboards up onto a shelf. So we would say that the 12th grader is intrinsically stronger than the 6th grader. In other words, just comparing equal numbers, the 12th grader is stronger. These represent the intrinsic strength of 6th and 12th graders. This is comparable to the Ka value for an acid. It compares equal amounts. But which can lift more skateboards? 6th graders or 12th graders, in other words, more than one. Now you need to know how many 6th graders and how many 12th graders. So if we have 18 6th graders, they will be able to place more skateboards onto the shelf than 2 12th graders. This represents how pH works. pH depends on both the intrinsic strength of the acid, the Ka value, but also on how much of it do you use, the amount of acid measured in molar concentration. So if you use a whole lot of a weak acid, it can produce more hydronium ions, H3O+ ions in the water solution than a small, tiny amount of a strong acid. So it depends on how much you use for pH. So summary, Ka is a characteristic of the acid only. The Ka value indicates which acid is stronger if you have equal amounts, molar concentrations. High Ka represents a stronger acid because the H+ ions dissociate more. pH is a characteristic of the solution, that's the acid and the water together. pH represents the concentration of hydronium H+ ions per liter of water and depends on, first of all, the strength of the acid Ka, but also the amount used, molar concentration. Low pH represents a more acidic solution. In other words, numbers down on the low end of the pH scale, 0 and 1, are more acidic. Numbers at the high end, 12 and 13 and 14, are very low acidity. They have very little acidity in it, very few hydronium ions. The same comparison applies for the pOH and molar concentration. So the higher on the pH scale, the stronger the base, 12, 13, 14. The relationship between Ka and Kb for a conjugate acid-base pair only is given by the equation Kw, that's the auto-ionization constant for water, equals the Ka times the Kb. So, and the Kw is 10 to the minus 14th at 25 degrees centigrade. So the following is an acid reaction for acetic acid. Acid reactions use Ka. So there it is. There's the reaction for acetic acid. It donates that H on the end to the water molecule to become H3O and COO, H3COO minus. That's the acetate ion. So that's the conjugate base. They differ from each other by one proton, that one H. And that has a Ka value of 1.8 times 10 to the negative 5th at 25 degrees centigrade. The reverse reaction is the base reaction. And to analyze a base reaction, Kb is required. So you simply do a little math. Kb equals Kw over Ka. You just solved for Kb. So you have 10 to the minus 14th over 1.8 times 10 to the minus 5th, and that gives you 5.6 times 10 to the minus 10th. So there's the reverse reaction of the one above. That's a base reaction. What it is a base that's at the acetate ion, CH3COO minus, taking a proton away from the hydronium in this case, and that turns the hydronium back into a water molecule and turns the acetate ion back into an acetic acid molecule. And so that reaction is going to have a Kb, because it's a base reaction, of 5.6 times 10 to the negative 10th. So if you multiplied 1.8 times 10 to the negative 5th times 5.6 times 10 to the negative 10th, you end up with 10 to the negative 14. If analyzing a base reaction and given a Ka, you must convert to the Kb. So you have to do this little math operation you see down here on the bottom to get it to a Kb before you can do that reaction if it's a base reaction. Okay, so the auto-ionization of water, there it is. We've seen this before. Now, that's at 25 degrees. It's 10 to the negative 14th at 25 degrees. The value of Kw increases with increasing temperature. And you can see over on the right. So at temperature 25, you see it's 1.00 times 10 to the negative 14th. But as you go to higher temperatures, the coefficient goes up. It increases. If the temperature is not 25 degrees, then the value shown on the right should be used depending on the temperature. So as temperature increases, more water molecules have the energy to auto-ionize. That is, for the proton to break away from the water molecule and create a hydronium ion and a hydroxide ion. However, it's still a very temporary situation. They will very quickly be put back together into a water molecule. That situation does not last for very long. Okay, so now we're going to do a rice table for acids and bases. This is our first one, and we're going to start with a strong acid. So we will set up a rice table for the strong acid, HCl, hydrochloric acid, of 0.4 molar concentration to see how many H3O plus we obtain from 0.4 molar of HCl. So you start off with 0.4 molar of HCl. You don't use water. It's a pure liquid. It's not used in a law of mass action and equilibrium equation. And you start off with no H3O plus and no chloride ion Cl minus to start. Now you're going to do minus X. One thing that makes acid and base reactions nice as far as rice tables is the coefficients are almost always ones, and that makes the calculations easier. So HCl has a coefficient of 1, so it's minus 1x, or we'll just say minus X. And for the H3O plus, it's plus X, and for the Cl minus, it's also plus X. Now we know what these numbers are going to be. We said the HCl is going to totally dissociate. That means that there's going to be no HCl at the end of this reaction. And what you're going to end up with is 0.4 molar of H3O plus and 0.4 molar of Cl minus. So the H breaks off into 0.4 molar and the Cl minus breaks off into 0.4 molar. So you have 0.4 molar all the way across. So over on the left side it becomes 0. You have no HCl left. You have 0.4 molar of hydronium H3O plus, and you have 0.4 molar of the chloride. So all 0.4 molar of HCl dissociated to 0.4 molar of H3O plus and 0.4 molar of Cl minus. A strong acid reaction goes from 100% reactants, that's the HCl, to 100% products, that's everything on the right side of the arrow. Since 100% of a strong acid dissociates to form H3O+, there's no need for a Rice table when using a strong acid. In other words, however many molar of the strong acid you're given, in this case 0.4 molar of HCl, you're going to end up with that same molar of hydronium ions, 0.4 molar of H3O+. So you don't need to use a Rice table for a strong acid. Now, a weak acid is a different situation, so let's do one for this weak acid right here. So this is going to be acetic acid. So we will set up a Rice table for the weak acid, acetic acid, of 2.1 molar concentration, and there's the Ka that you've seen before for acetic acid. Again, that's a number you can look up in Google or in a textbook, a chemistry textbook, at 25 degrees. Okay, and now what we're going to do here, step 1, complete the reaction with the acid donating a proton to water to create H3O+ and enter the initial concentration of each reactant. So we're going to go ahead and do that. We start off with 2.1 molar acetic acid. We don't count the water, and we start off with 0 molar of H3O+ and of the acetate ion. That's CH3COO-. That's the conjugate base of acetic acid. Okay, since no concentration values are given for H3O+ and Cl-, we can assume they are 0. And now we'll move on to step 2. So now enter the variable x on the change line with coefficients plus and minus sign as necessary. So on the left side it's minus 1x because acetic acid has a coefficient of 1. The hydronium ion H3O+ has a coefficient of 1, and the acetate ion has a coefficient of 1. So minus signs on the reactant side because it's decreasing in concentration, and plus signs on the product side because it's increasing in concentration. So the reactant CH3COOH shows a negative sign because it is decreasing in concentration. The coefficients in front of the X variables are the same as in front of the reactant and product reactions above, which are all 1s. Water is not included since it is pure liquid. Okay, 3. Add, subtract the change line from the initial line to obtain the equilibrium. So the equilibrium below on the reactant side is going to be 2.1. Over on the product side, it's going to be 0 plus x is x, and 0 plus x is x. Step 4. Write the law of mass action, the equilibrium equation for the reaction. So there it is. Convince yourself that that's correct. The products go on the top, you multiply them together, the concentrations, the reactants on the bottom, and you don't include water because it's a pure liquid. Now we're going to substitute in the algebraic expressions. So substitute the algebraic expressions on the equilibrium line into the equation. And this is what it's going to look like. Also, you know what the Ka value is, so we're going to substitute that in as well. And there it is. Ka is 1.8 times 10 to the negative 5 equals x times x on the top. Those are the products. And the reactant 2.1 minus x on the bottom. That's the reactant. Okay, now the simplifying assumption states that if the value of x is much smaller than the initial concentration, 2.1 molar, and we're going to always assume that it is, then x in the 2.1 minus x can be eliminated. So we're going to go ahead, and you have to eventually justify that at the very end by using the 5% rule. Okay, so 1.8 times 10 to the negative 5th, there you have what we saw in the previous slide. Now we're going to eliminate the x in the denominator, and we're going to put the x's on the numerator together to make x squared. So that's what you have. Be sure you understand that. Okay, now we're going to solve for x. So there we have that. You multiply both sides by 2.1. You cancel on the right. You come over here and you get x squared equals 3.78 times 10 to the negative 5th. Now you take the square root of both sides, and you end up with X equals 6.15 times 10 to the negative 3. So that's the molar concentration of H3O, because up on the equilibrium line of the rice table, the equilibrium concentration of H3O plus is X. It's also the equilibrium concentration of the acetate ion, CH3COO minus. And so now we're going to figure out for acetic acid how much we have left. So calculate the concentrations. You might be interested in only one concentration. That's often true. So CH3COOH is the 2.1 minus X, which is minus 6.15 times 10 to the negative third, and that gives you 2.09. So in other words, you went from 2.10 down to 2.09. That's a decrease of only 1/100th molar concentration. So you didn't lose very much of your acetic acid. And then the H3O plus equals X. Again, you just look at the equilibrium line of the rice table, and that's 6.15 times 10 to the negative 3, what we just calculated. And the same is true of the acetate ion, is going to be that same value. So only a very small fraction of the original CH3COOH concentration dissociated to hydronium and the acetate ion. Okay, step 9, calculate OH minus, pH, and POH. You might not always be asked to do this in a problem, but I call these the big four. Hydronium ion concentration, hydroxide ion concentration, pH, and POH. So you want to know that you can calculate all four of those, okay? So let's go ahead and do that. So for the OH concentration, you have the formula you learned in an earlier lesson of H3O plus times OH minus equals 10 to the negative 14th at 25 degrees. So if you do a little manipulation there, OH minus is going to equal 10 to the minus 14th over the H3O concentration. And that's going to be 6.15 times 10 to the negative 3. Do the math on that, and you get the hydroxide ion concentration of 1.6 times 10 to the negative 12th. And that should be molar with a big M after it. So that's a very tiny number. Now for the pH. pH is negative log of the hydronium ion concentration. We learned that in the last lesson. So it's negative log of 6.15 times 10 to the negative third, and that's 2.2. That's not quite a strong acid. It would have to be down around 0 or 1 to be a strong acid, but it's a pretty strong weak acid. So it's on the strong end of the weak acids. And then finally, to get POH, you'd simply POH plus pH equals 14. So you subtract the pH from both sides, 14 minus 2.2, and you get 11.8 for the POH. And there it is. And that takes care of our lesson on weak acids. In the next lesson, we'll learn how to deal with weak base situations, and those are essentially the same.